This video lesson is on quality control. QA stands for quality assurance and QC stands for quality control. Policies and procedures ensure that patients are exposed to minimum radiation. They also ensure that we produce optimum image quality for diagnosis and finally reduce cost of operation. A QA program, which again stands for quality assurance, are systems and procedures for assuring quality patient care. They involve things like quality assessment, continuing education, usefulness of QC procedures, assessment of outcomes, and administrative aspects of patient care and quality outcomes. The Joint Commission's 10-step quality assurance program begins with assigning responsibility, then delineating the scope of care, then identifying aspects of care. And you can read down through the list, but the one final thing is communicating information to organization-wide quality assurance programs is the final step. On the QC program, which again is quality control, it's about monitoring equipment to maintain quality standards. It ensures that the radiologist is provided with an optimal image produced through good imaging system performance and resulting in minimal patient radiation dose. We want to recognize and report malfunctions also. So monitoring equipment performance involves acceptance testing, which is performed by a physicist and performed on new equipment or on equipment that's undergone major repair to ensure it's performing at manufacturer specification. Secondly, we have routine performance, which is conducting QC tests on equipment on a regular basis with varying degrees of frequency, whether it be annually, semi-annually, monthly, weekly, or daily. And finally, error correction, which ensures that equipment not meeting the performance criteria or tolerance limit established for specific QC tests must be replaced or repaired to meet specifications. QC tests should include regular documentation of imaging frequency, imaging performance, and condition of each imaging plate and flat panel detector. The QC program is required for records for legal reasons, for insurance carriers, and for accreditation, specifically the Department of Health and the American College of Radiology. When purchasing new equipment, we want to identify imaging requirements. Secondly, develop equipment specifications, select the equipment, then install and do the acceptance testing, which would be performed by the physicist, then do continuing education for the technologist, monitor the equipment performance, and then from there would be processing systems and external beam evaluations. Visual inspection, which is performed annually, is on the control panel, the overhead tube crane, the radiographic table, protective apparel, and miscellaneous equipment such as sponges, step stools, IV stands, and equipment free of contrast media, etc. So this chart is something that you can complete after going to the video, and it's also in your worksheet. So the quality control test on the filtration, this test tool is at the half value layer. We use an X-ray tube, aluminum absorbers, and a digital dosimeter. The accuracy is greater than or equal to 2.5 millimeters of aluminum, and the frequency is annually. So on the left-hand side, we take an exposure without any aluminum in the path. Then we take an exposure with aluminum in the path on the right, and then the actual radiation dose to the detector would be cut in half, which is why it's called the half value layer. And then the approximate relationship between KVP and the half value layer is that as you increase KVP, the half value layer also increases. So they're directly proportional. For beam restriction, the X-ray field must coincide with the light field of the variable aperture light localizing collimator. The type specifically are manual collimators and PBL. Accuracy must be within plus or minus 2% of the SID. The frequency is semi-annually. There are two tests that could be used for beam restriction, and the first one is called the collimator test tool. That's the one that's on the left. The name of it is actually right here on this plate. And the one on the right is called the penny test because 8 pennies are used. For distance and centering, we have a distance indicator test, which is called the tape measure, and the accuracy for SID must be within plus or minus 2% of the SID. We also have accuracy required for the centering, and that's a centering indicator. This one's visually checked, or we can use the collimator test tool for it, and the accuracy is within plus or minus 1% of the SID. On the left-hand side is the collimator test tool with the plastic piece that's in the center. It has a dot in the center, which shows up radiographically in the center, and that's going to check the centering indicator. And then you can also see that there are two exposures that are taken, and one is taken with the entire cassette, oops, the entire tray or whatever, and then here's the center part of it. And we're to check to see if the collimation is off by plus or minus 2%. We can see the top image is actually in really good shape, but the bottom image is off by likely by more than 2% to the SID. The focal spot size test tool measures spatial resolution, and that's because focal spot size only affects spatial resolution. The QC tools are the pinhole camera, the star pattern, and the slit camera. Accuracy is plus or minus 50%. The frequency is annually whenever an X-ray tube is replaced. These are pictures of the star pattern test tools, and the process is to take an exposure of the image and to analyze the image to measure the focal spot size. The line pair test measures spatial resolution, and the test tool is a line pair test pattern. So we're going to take an image of this test tool device and visually look at the image to see how many lines can be seen. For KVP calibration, one of the tools is the digital dosimeter. An oscilloscope could also be used, which is going to be able to look at the wave pattern itself. The accuracy is plus or minus 10%, and the frequency is annually. For the exposure timer accuracy, the test tool is a digital dosimeter. The accuracy is plus or minus 20% for exposure times of 10 milliseconds or less, and plus or minus 5% for exposure times are greater than 10 milliseconds. The frequency is annually or more frequently if a component of the operating console or the high voltage generators undergone major repairs. Exposure linearity is going to also use the digital dosimeter. We're going to take exposures using different MA and different time stations that equal the same mass. And the accuracy has to be within plus or minus 10%. This is performed annually or after any significant change or repair of the operating console or high voltage generator is made. Exposure reproducibility also uses the digital dosimeter, and accuracy for this is plus or minus 5%. The frequency is annually for this test tool as well. And for this one, we're going to use the exact same MA at the exact same time and get the same mass. And that's the result is get the same exposure on the image. Protective apparel has to be also monitored, and it's by radiography or fluoroscopy. The frequency is annually. And we're going to look for dark areas that we should not see on the image. Repeat analysis should be performed monthly and should be within 1 to 3%. The AAPM recommends that 8% be used as a target for overall rejected image rates, and that 10% be used as a target for investigation and possible corrective action. Digital QC program is performed routinely by the QC technologist, and as the routine procedures that are performed would be on the protective apparel and also on the repeat analysis. Full inspection is performed by the medical physicist and involves radiation measurements and non-invasive adjustments. And system adjustment is performed by the vendor service personnel and involves hardware and software maintenance. For CR system inspection, the general inspection should be performed daily. We want to erase imaging plates before use daily. Imaging plate loading and unloading mechanisms in the CR reader should be cleaned and lubricated at least weekly. There should be we should clean the eyepiece with a dry cloth in our cleaning solution, not water-based, and avoid dust and dirt on imaging plates also. And then finally, clean and inspect for hairline cracks monthly. This is an example where there's damage to a CR cassette, and the image on the left-hand side showing the effect on the image or the impact it could have on an image. DR system inspections, the general inspection should be daily. We should keep the DR cassettes clean and free of dirt and debris, blood, contrast media, etc., and inspect for scratches weekly. Clean and view for cracks monthly. And the batteries, internal batteries in the wireless flat panel detectors should be inspected to ensure that they're fully charged. And that should be at all times. Uniformity test is going to evaluate uniformity of image brightness across CR scanning with or active matrix array for digital radiography. The test pattern is the LEEDS MS4. It's viewed after processing, and it confirms CR reader light guide position and optics, and the LEED software can correct for non-uniformity. On the left is the LEEDS test kit, and on the right is an image from the LEEDS test. Erasure thoroughness must be evaluated with CR and DR. In the case of the CR, it must be viewed daily just to evaluate to see if the cassettes were completely erased. And with DR, we're going to ensure that the flat panel detectors release all the charge before the next exposure. For erasure thoroughness, the test is to create an image of the metal in the LEEDS test kit at extremely overexposure, F500 microgray, and process the imaging plate. Take a second exposure of the same plate with a 50 microgray exposure and analyze the second image for the presence of the first one. Exposure indicator calibration, it's going to determine accuracy. You would expose a digital dosimeter and compare the value with the manufacturer's EI system. The variation between the stated value and the actual value should be less than 10%. So now we have digital display device items to look at. Performance assessment standards, luminance meter, the digital display device for QC, and the QC by the radiologic technologist. The SMPTE pattern is going to measure display resolution and grayscale uniformity. It points out any gross deviations in luminance adjustments and involves a 10-step grayscale that can be used to construct a characteristic curve to monitor grayscale performance over time. It was developed by the Society of Motion Picture and Television Engineers. DICOM GSDF is a standard that specifies a function that relates pixel values to displayed luminance levels, and images have a consistent grayscale appearance. AAPM TG18 are a series of test patterns developed by the AAPM. TG stands for task group, and 18 is just the number that they're on. They're required by the American College of Radiology, and they're used to perform most of the QC tests on digital display devices. There's a luminance meter, which is also known as the photometer. There are two types, the near-range photometer, testing close-range monitors, and there's a telescope photometer, which tests from a distance of 1 meter. Photometric evaluation of digital display devices at ambient light levels is essential to digital QC. The accuracy should be able to measure luminance in the range of 0.05 to 1,000 candelas per meter squared with better than 5% accuracy and a precision of at least 0.01. The TG18QC test pattern is used for geometric distortion and grayscale uniformity. It looks for variation in the distortion, which is size and shape of the displayed image from the original, and all lines in the pattern should appear straight. The tolerance is 2%. For reflection, we're going to evaluate an ambient light contribution to the light reflected by the display device. This display device reflection can be specular or diffuse. Monochrome CRT is reduced reflection because of an improved anti-reflective coating. A simple test to assess for specular reflection is to turn off the monitor and look for sources of illumination within a 15-degree angle of observation at a distance of 30 to 50 centimeters. Another method used to measure reflection is to use the TG18AD test pattern. It's uniformly varying low contrast patterns and observe low contrast patterns under ambient lighting and total darkness. There are two tests that can be used for luminance response, and that's the TG18CT test pattern. This is a qualitative evaluation of luminance response of a digital display device. The test pattern has low contrast targets that should be visible in all 16 regions of the pattern. The pattern should be evaluated from a distance of approximately 30 centimeters. The TG18LN test pattern, it can be used with the use of external photometer, is going to assess displayed luminance values versus the input values from the display system. And this is a picture of the TG18CT test pattern. And this is a picture of the TG18LN test pattern. There's also luminance non-uniformity that can be measured with the TG18UN and UNL test patterns. They evaluate for non-uniformity and effects of viewing at various angles. And here's one for here's the UNL. The TG18CX test pattern evaluates display resolution. The CX patterns in the middle of the corners can be evaluated with the magnifying glass and compared. And here's the PX test pattern. It's for resolution uniformity. Display noise can be evaluated with the AFC test pattern. For display evaluation, we have the TG18CH test pattern that evaluates the overall system display, and it's going to have a chest pattern in it and for evaluation. And this concludes our video lesson on quality control.